Um, Imagine a single microscopic flaw in a line of code just completely ruining a multi-million-dollar microchip manufacturing run.
Right. Which happens.
Exactly. I mean, when you're building the software that actually designs our hardware, you absolutely cannot afford a single mistake. So when it comes time to build those systems, do you rely on traditional steel, like C++
Basically
stores?
is your standard.
Yeah, the stuff that's held up the industry for decades, but definitely lets you make dangerous mistakes if you aren't perfectly careful. Or do you use a hyper advanced, mathematically rigorous composite material like rust?
Which is great, but it refuses to compile if there is a flaw.
Right. It might just be too stubborn to bend the way your architecture actually requires.
And that tension right there, that's driving one of the most intense architectural debates in software engineering today. I mean, you are dealing with multi-year engineering investments, complex onboarding for new hires, strict runtime performance metrics, and obviously the need for absolute correctness and safety critical systems.
Which brings us to our mission for this deep dive. We are cutting through all the usual theoretical arguments today and looking at an incredibly detailed empirical study. This was published by developer Lux036 back in 2026.
It's a fascinating piece of work.
It really is. And it explores the Rust versus C++ choice, specifically in the context of EDA tool development. Now, for those who might not be deep in the hardware weeds, EDA stands for Electronic Design Automation.
Basically, the foundational software platforms used to physically lay out and design microchips.
Exactly. So whether you are a tech lead making stack decisions for your own team, or you're just intensely curious about how AI is reshaping the way we build software. And trust me, we have a massive plot twist regarding AI coming up later. This data is going to challenge some of your fundamental assumptions.
Oh, absolutely. Because the stakes in EDA are just astronomical. The software performs incredibly complex geometric math, things like polygon decomposition and calculating interval overlaps across billions of transistors.
Brilliant. So it's not a small task.
Not at all. A single memory bug, literally one stray pointer that points to the wrong address in memory, it corrupts the entire output. That could mean a flawed production router or a whole batch of dead processors. So eliminating the guesswork of whether a language is actually safer or faster isn't just an academic exercise here. It is an absolute industrial necessity.
Right. And the author of this study did something remarkable to figure this out.
Yeah.
They didn't just compare random open source projects, which is what usually happens in these debates. They created what they call sibling code bases.
Yeah, and that methodology is exactly what makes this data so compelling. To get a true apples to apples comparison, the author built identical geometric EDA libraries entirely from scratch.
Wow, from scratch.
Yep. The Rust version is called FISD's Bastars, and the C++ version is FISD's CPP. And they use the exact same algorithms implemented to achieve the exact same goals.
So it's kind of like having the exact same master architect design two identical houses, but forcing them to use completely different physics engines to build them.
Yeah.
We completely eliminate the whole, different programmer or different algorithm variables.
Exactly. If one is slower, it is the language's fault, not the developers.
That is such a clean way to test it.
It is. And looking at the sheer scale of the resulting laboratory setup already tells a fascinating story. I mean, the Rust code base sits at about 5,200 lines of code. And importantly, that includes all of the testing infrastructure.
Okay, 5,200 lines.
Yeah, and it runs on a remarkably clean 40-line cargo build system.
That's nothing. 40 lines is tiny.
Right. Now, the C++ version is actually a bit smaller in terms of raw logic. It's sitting around 3,500 lines of headers and implementation files, but it relies on a highly complex, multi-layered CMake and XMake build system.
Oh, man. I mean, anyone who has maintained a legacy C+ code base is probably nodding along right now. The build systems alone can practically require their own dedicated engineering teams.
Oh, definitely. CMake can be a nightmare.
But let's get into the most critical metric. Once that code is actually written and compiled, the very first thing an EDA developer cares about is raw speed, especially in these hot computing kernels that have to run calculations millions of times a second.
Speed is everything in this space.
Right. And there is this lingering assumption in the industry, I hear called the safety tax a lot, that because Rust forces all these intense memory checks, it inherently must slow down the software.
Yeah, that is a very persistent myth, but the data from these sibling code bases completely shatters it. Let's just look at the actual dispatch costs.
Okay.
So dispatch is simply the time it takes for the program to figure out which function it needs to call and then actually execute it. In C++, say, using a standard free function, it takes 1.54 nanoseconds.
Okay, 1.54 nanoseconds for C++1. And a Rust sibling.
In Rust, utilizing something called trait monomorphization, it takes 1.61 nanoseconds.
Wait, 1.61. That's barely a difference. But let's unpack that term for a second, because trait monomorphization sounds incredibly dense.
It's a mouthful, yeah.
My understanding is that instead of the program wasting time during runtime trying to figure out if it's dealing with, say, an integer or a decimal, the Rust compiler does all the heavy lifting beforehand. It basically generates a completely separate hard-coded version of that function for every single data type you use. Is that right?
That is a great way to visualize it, yeah. Because the compiler generates those specific hard-coded copies, the CPU doesn't have to pause and look up instructions dynamically. It just executes the specific path built for that exact data type.
So it's basically pre-planned.
Exactly. And the resulting machine code for Rust's static dispatch is practically identical to the C++ output. The difference between 1.54 and 1.61 nanoseconds is essentially within the margin of noise for standard hardware testing.
That's wild.
Now, if you force Rust to use dynamic dispatch, where it actually has to use a virtual table to figure out the type at runtime, it takes about 2.90 nanoseconds.
So roughly twice as slow.
Right. But as long as you architect around static dispatch, there is absolutely zero speed penalty.
Okay, so you've sold me on the raw function speed. But what about error handling? Because, Rust is famous for forcing the developer to explicitly handle every single possible error before it will even let you compile.
True.
And in an EDA tool, you are constantly checking for design rule checking violations, or DRC violations, right?
Constantly.
Now, C++ usually handles these with runtime assertions. It basically just runs until it hits a wall and then throws a flag. Rust handles this with algebraic data types using enums and pattern matching.
Right, which means in Rust, those DRC violations are locked directly into the type system itself. You physically cannot compile the program if you haven't written logic to handle the possibility of a failure.
See, this actually shifts my entire perspective. We are so conditioned to believe that exhaustive safety checks must require some sort of computational overhead. I just assumed that all that pattern matching and returning complex result enums would bloat the runtime. I mean, does a geometry result in a hot loop cost more just to carry that safety guarantee?
That's the crazy part. The empirical data proves it costs absolutely nothing.
Nothing at all.
Zero. When the author measured the success path, so that's the happy path where the geometry math executes without hitting any design violations, the C++ runtime assertion took exactly 4.36 nanoseconds.
Okay.
The Rust version, using exhaustive pattern matching and a result enum, took precisely 4.36 nanoseconds. Every variation they tried compiled down to identical machine code instructions.
That is just astonishing. Zero cost abstraction is actually real. I mean, the compiler is doing all the paranoid safety checking on its own time before the program ever launches.
Yes, exactly.
So you get software that is objectively safer, mathematically preventing production crashes without sacrificing a single nanosecond of runtime performance.
It is a massive win for Rust. But if you are a tech lead listening to this and thinking you should instantly rewrite your entire tech stack, hold on.
Yeah, there's always a catch, right?
Always. Because software architecture is about way more than just crunching numbers in a straight line. It is fundamentally about data structures, how you organize and link information in memory. And this is exactly where Rust hits a profound structural speed bump.
Right, because crunching numbers is only half the battle.
Right.
An EDA tool analyzing a microchip is basically navigating a giant, complex web of connected shapes. And I saw in the source notes that the dreaded linked list becomes a major problem here. Let's break down the mechanics of this because I think it highlights a fundamental clash in programming philosophies.
It really does. So in EDA, when you are performing polygon decomposition, which means taking complex overlapping shapes and breaking them down into simpler, manageable rectangles, you rely heavily on doubly linked lists.
Okay.
These lists allow the algorithm to instantly insert or remove nodes on the fly as it slices up the geometry. The core tension here is that Rust's defining safety feature, the borrow checker, fundamentally assumes your computer's memory is structured as a directed acyclic graph, or a JAG.
A DAG. Okay. Acyclic, meaning no loops. Best analogy I can think of is like a traditional family tree. I point to my children, and my children point to their children, but my children don't point back up the tree to make me their child.
Right. That would be weird.
Very weird. The flow of ownership only goes in one direction.
The family tree is a perfect way to look at it. Because ownership only flows one way, the Rust compiler always knows exactly who is responsible for cleaning up the memory when a node is deleted. But a doubly linked list is inherently cyclic. It's a circle.
Okay.
Node A points to node B, and node B points right back to node A.
Ah, so if you try to delete them, the borrow checker just panics because it can't figure out who owns who. Node A says, well, I can't be deleted, B needs me. And B says, I can't be deleted, A needs me.
Exactly. It creates a complete deadlock.
So how does C++ handle this? I mean, legacy EDA tools have been doing this exact math for decades.
Oh, C++ handles cyclic graphs using a brilliant low-level optimization called a sentinel trick.
A sentinel trick.
Yeah. When a node in the list is temporarily locked or isolated by the algorithm, instead of its pointer pointing to null or nothing, it simply points to itself. The pointers are always valid memory addresses.
Wait, why does pointing to itself matter so much for speed? I don't quite get that.
Okay, so think of a modern CPU like a high-speed train on a track. Modern processors use something called pipeline prediction. They guess what the next instruction will be and start executing it early to save time.
Right.
If your code has an if statement checking, hey, is this pointer null? Is this the end of the list?
Yeah.
You are basically putting a fork in the train tracks. The CPU has to stop, evaluate the fork, and risk a pipeline stall if it guesses wrong.
Oh, I see.
But by using a sentinel node that points to itself, there are no null checks. There are no forks in the track. The CPU just blasts forward at maximum speed without ever branching.
That is incredibly clever. But Rust cannot do that safely, right?
Not at all. Rust categorically rejects the self-referential sentinel trick. It violates the core tenets of the borrow checker. To build a doubly linked list in Rust, you are forced to use explicit null pointer checks, which introduces those branching slowdowns.
Those forks in the track.
Exactly. And more importantly, because you are building a cyclic graph, you have to bypass the borrow checker entirely using the unsafe keyword. You are stripping away the compiler's protection and telling it, trust me, I will manage the memory manually.
Which kind of defeats the whole premise of using an ultra-safe, compiler-verified language in the first place. I mean, if you have to turn the safety off in the most critical, highly trafficked loops of your geometry engine, what is the point?
That's the million-dollar question.
The author of the study tried to engineer a purely safe workaround for this, didn't they?
They did. They built an alternative data structure called an arena index to see if they could avoid raw pointers entirely.
An arena index.
Yeah.
How does that work?
So instead of nodes pointing directly to physical memory addresses, every node simply points to an index number like row 5, seat 12 within a giant pre-allocated array or an arena.
Oh, okay. And the performance result of that.
Well, the good news is that it achieved zero unsafe code. It completely satisfied the compiler.
Right.
The bad news is the performance tanked. It resulted in a 36% slower traversal time. To put hard numbers to it, traversing a 1,000 node circular list took 4.96 microseconds using the safe arena index, compared to just 3.66 microseconds using raw C++ pointers.
Let me push back on this a bit, because that sounds like a fatal flaw for Rust in the specific industry. You are forcing a tech lead to make a terrible choice. You either accept a massive 36% speed penalty in your most performance-critical code, or you write unsafe raw pointers and manually manage memory, effectively turning Rust into a more difficult version of C++. Is there a third option?
There is, actually, and the author found a highly effective mitigation. You see, the real enemy of speed here isn't just the pointer traversal, it is memory reallocation.
Reallocation, meaning moving things around.
Right. If you use a standard vector in Rust to hold your nodes, and that vector fills up its current memory block, the operating system has to find a new, larger block of memory, copy everything over, and destroy the old block.
And if you're using raw pointers, moving that memory invalidates every single pointer instantly, right? Causing a catastrophic crash.
Exactly. It's a nightmare.
So how do you stop the vector from moving?
By heavily over-reserving memory right at the start. The study found that if you pre-reserve exactly 3 times the capacity you think you will need for the polygon decomposition, you prevent the vector from ever needing to reallocate.
3 times the capacity. It seems like a lot of wasted RAM.
You do waste a little bit of RAM, yeah. But that simple trick sped up the Rust process by 79%. It brought the raw pointer implementation down to 2.0 microseconds for a 50 vertex decomposition, making it highly competitive with the C++ speeds.
Okay, so a highly skilled human developer armed with this data can navigate these architectural quirks. They can pre-allocate memory buffers and, strategically isolate their unsafe blocks. But we need to pivot to the massive plot twist in this source material.
Yes. The twist.
Because this wasn't just a test of human developers.
No, the human element is entirely removed from the actual code generation in this study.
This blew my mind. This entire 8,000 plus line sibling code base experiment was synced, generated, and iteratively written by an AI agent. Specifically, the author used the OpenCode framework powered by the DeepSeek V4 Flash model.
It's wild.
So the dynamic of this entire debate completely shifts. We're no longer just asking which language is better for a human to read. We're asking how do these two languages compare when the programmer is a machine?
And it forces us to view programming languages through an entirely new lens. When an AI agent writes code, it doesn't rely on intuition or Stack Overflow searches like we do. It operates strictly on a token economy.
Token economy.
Yeah, an AI has a hard limit on its context window. Basically,
Right.
its memory budget for a single conversation. Every rule it has to remember, every line of a build file, every complex error message, it all burns through that token budget.
So let's break down that token economy, because the empirical data here is just staggering. Before the AI could even write a single line of C++ logic, what did the author have to feed it just to set the ground rules?
Well, to get the AI to successfully navigate the C++ environment, the context file was 442 lines long.
442 lines just of instruction.
Exactly. The AI had to digest the complex CMake hierarchy, memorize 43 separate Clang-tidy formatting rules, and understand distinct convoluted build commands for testing versus standalone execution.
Why is that? I mean, is it because in C++ day that AI has to manually become the memory manager? Like it has to keep a running tally of every thread, every object lifetime, every ghost of a deleted variable, otherwise the code just seg faults.
That's a huge part of it, yes. It has to keep all those rules in its active memory.
And what was the context burden for the Rust code base?
Just 211 lines.
Less than half.
Less than half. Because the rules of Rust aren't something the AI has to manually simulate in its context window, they are rigidly baked into the compiler itself. The AI doesn't need to be told how to format code or manage dependencies because Rust's built-in tooling is universally standardized.
Which becomes incredibly obvious when you look at the build commands. I mean, if the AI wants to build the Rust project, it generates one token, that cargo build. If it wants to test, the cargo test.
It's so simple.
But to do the same in C++ Rust, it has to generate massive multi-token incantations with specific compiler flags and directory paths. If the AI hallucinates a single flag, the build fails, wasting an entire prompt iteration.
Oh, and the difference in error handling is even more profound. When the AI makes a logic mistake in Rust, the Rust compiler replies with a clear, highly localized error message and usually provides the exact line of code to fix it.
Which is super helpful for an AI.
Very. But when the AI makes a template mistake in C++ Rust, the compiler vomits out an opaque cascading backtrace.
So the AI has to burn even more of its precious tokens just trying to read and comprehend the C++ error message. It could potentially lose the context of what feature it was even trying to build in the first place.
It severely degrades the AI's productivity. And then you have to consider the physical layout of the files, too.
Right, the sandboxing.
Exactly. The study highlights a Rust pattern called the AA.R sandbox. In Rust, you can create these isolated sandbox files right next to the production code. The AI can experiment, write tests, and verify logic securely. Because of Rust's explicit module system, the boundary between the AI's playground and the main application is airtight.
While in the C++ architecture, there isn't really a native equivalent. If the AI tries a radical new implementation, it either risks corrupting the main code base or it has to operate in completely disconnected files.
Right. And Rust allows hashtag test tags right alongside the source code. The AI writes the function and the test in the same breath. In the C++ sibling code base, the study noted there were 27 separate test files scattered across an entirely different directory tree.
27 files. That's a lot of jumping around for an AI agent.
Too much. The core insight here is really about guardrails, who provides them. In C++ May, the compiler is lenient. It assumes the programmer, whether human or AI, knows exactly what they're doing.
Right.
So if the AI makes a subtle aliasing error or a thread safety mistake, the C++ compiler compiles it anyway. The bug isn't caught until runtime, if it is caught at all. The AI has no immediate feedback. But in Rust, the borrow checker acts like a merciless, incredibly strict senior developer standing right over the AI's shoulder. It catches aliasing and lifetime errors instantly at compile time.
And the data backs that up brilliantly.
Yeah.
Because of that immediate strict feedback loop, the AI in this study was able to self-correct complex logical issues in Rust within, what, 1 to 2 iterations?
Yep, 1 to 2 iterations.
And in C++ may, because the errors were opaque and the compiler let memory bugs slide, it took the AI 3 to 5 iterations to fix the exact same problems.
It's a huge efficiency gap. So, bring all of this empirical data back to our original mission. Should a tech lead rewrite their EDA architecture in Rust, or stick with the proven steel of C++ now?
$1 million question.
The verdict from the sibling code-based study is that it is absolutely not a binary choice.
Yeah, the data paints a very nuanced picture. Rust definitively wins on memory safety. You mathematically eliminate production seg faults. It wins massively on AI agent productivity and token efficiency.
Absolutely.
It has built-in fuzzing, which is vital when parsing weird, malformed chip layout files. And it offers fearless concurrency, meaning you can run parallel tasks across multiple CPU cores without data races.
But, and this is a big but, C++ still holds indispensable high ground. It possesses a massive, decades-old ecosystem. If you need an industry-standard parser for open access or Verilog, it is written in C++ MAU.
It's already there.
Right. It seamlessly handles legacy EDA code that is simply too vast and expensive to ever rewrite. And crucially, if your tool requires industry-standard GPU compute, like NVIDIA's CEA, that ecosystem is overwhelmingly built for C++ first.
So what is the pragmatic strategy moving forward? You obviously don't just pick one and abandon the other.
No, the winning pattern identified by the data is a hybrid approach. It relies heavily on FFI, or a foreign function interface.
FFI.
Yeah, FFI acts as a high-speed diplomatic translator between two different programming languages.
Meaning you can have them talk to each other in the same program.
Precisely. You unleash your AI agents to write all the new algorithmic and the complex new features in Rust. You get the fast AI iteration, the strict compiler verification, and the zero-cost dispatch speeds.
Okay.
Then, using FFI, you compile that Rust code into a library and plug it directly into your existing C++ infrastructure.
I love that. It perfectly upgrades our skyscraper analogy from earlier. You don't have to demolish a 50-story steel building just to use a better material. You keep the proven steel frame, the C++ ecosystem and all those GPU libraries, but you construct all the highly stressed new additions using the mathematically perfect composite material of Rust.
Exactly. You get the AI-friendly guardrails of Rust exactly where you need them without sacrificing the deep ecosystem access of C++A. It is the pragmatic best of both worlds.
It's a really elegant solution to an incredibly complex engineering problem. But, looking at the implications of this study, I want to leave you with the final thought to mull over.
Go for it.
We just saw, with hard data, how an AI agent struggled under the weight of C++'s complexity, yet thrived against Rust's strict token-efficient compiler. So if AI is inevitably going to take over the heavy lifting of writing and maintaining our code bases, will the programming languages of the next decade be designed for human readability at all? Or would they be engineered specifically for AI agent predictability and token efficiency?
That's a fascinating point.
It fundamentally changes what makes a language good. Something to think about the next time you sit down to write or prompt a line of code.